these lines.
No.
Let's think of it even more simple. They're just two rays. An angle is created, you're right, two lines create angles, but more specific, if I'm looking at just one angle is created by the intersection of two rays. Those two rays have the same endpoint. Remember, rays are written like, oh, that's not working. If I say it's ray BA and ray BC, what do those two rays have in common? B. They have a common endpoint. So angles are created by having two different rays that have the same endpoint, like that. Oh, that's it. Two rays with a common endpoint create an angle. Now, I know that you guys have seen that before. I know that's not new. But what's going to be new is kind of how we write out angles. How do we label them? How do we work with them? How many letters do you need to have? Things like that. When you have angles, you need to use 3 letters. Okay? And that's why I put a little asterisk here about how you label these things. When we're talking about angles, we talk about we use 3 letters for them. In this case here, what's the common endpoint that they have? B. That common endpoint where the rays change direction, this spot right here, is called the vertex. The common endpoint of an angle is the vertex. It's where the rays change direction. It's where the rays change direction. And then obviously the sides of the angle are just the rays. So we don't do a lot with the sides part, but we deal a lot with the angles. When we label them, we use 3 letters for angles, and the middle letter is always the vertex. So we say this is different than how the book does it. I grew up when I was in high school geometry. The way that I was taught is kind of the way that I've always taught it, because I thought it was a little bit cleaner, the way that we use a symbol for angle. Because writing the word angle is just too many letters. We do this. And I put a little arc in it. Okay? The reason I put that little arc in there, because if I don't, what does it look like?
A greater than L.
Yeah, it looks like a less than symbol or a greater than symbol. It looks like an L. So by putting that little arc in it, it shows that it's an angle. Plus, remember when we dealt with, oh man, my eyes killed me. Plus, remember when we dealt with the compass? When you create the angles, we're using an arc to measure stuff out. It's kind of the same idea. Okay? So I would say this would be angle ABC, where this middle letter is always the vertex. The other 2 letters just tell what direction you're working, what direction you're reading the angle from. Is ABC the same thing as CBA? Yes. Yes, they're the same angle. Going this direction or this direction is the same way, because B is still in the middle. Just the same as if we said that we had segment XY, isn't that the same as YX? It just means you just go the other direction, okay? Angles can be written going either direction. It does, as long as the middle letter is your vertex, you're fine. Now, there is one other way that you can label out your angles as well. It happens about 10% of the time that it works out cleanly. You can always label an angle, if it's possible, with 1 letter, just the vertex, because sometimes this is the only angle that has B as a vertex, so I can call it angle B. But there are other times that it doesn't work like that. Okay? There are other times that if you have let's say this is point B again. We'll say this is A, C, D, E, F, G. Can I call any one of those angle B? No, I can't. Because angle B is the vertex for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's so many different ways that you can use angle B as the vertex. Only use one letter if that vertex is the only one it can be. Does that make sense? So angles, you'll never be wrong if you use 3 letters. You could be wrong if you use 1 letter. You will always be wrong if you use 2 letters, because angles aren't segments. And then segments aren't angles. It's very exciting. Yay! Okay. Question on any of that? Pretty straightforward, I'm hoping? Anybody ever see that before when you guys talk about angles back in middle school at all? The little arc. I know most teachers just use that.
Yeah.
Is it okay that with this? Is it okay that I use that?
No.
It's just one of those things. I mean, if you don't use it, it's not a big deal. It's the same thing. It's just when I grew up, that's just how I was taught, and it just stuck in my brain. That's all. I don't think any other math teachers here even use that, to tell you the truth. So this allows us to, there are 4 ways to classify angles by their measurement. There are 4 ways to classify your angles by their measurements. Now, I know that you have all done this. This is absolutely not new. What I'm basically asking you here is, what are the 4 types of angles? First of all, how do you measure angles? Do you remember? What do you measure them in? Degrees, good. In geometry, we measure all of our angles in degrees. Algebra 2, we'll start talking about things that are called radians. You ever notice on your calculator the button that you'll sometimes hit, it says rad? You know what I'm talking about?
The radical?
Not the radical, but there's a mode on your calculators that says radian, or it says rad. The very top row of that, it should say mode, I think.
Oh, it's here.
You see how it says rad?
Yeah.
Rad isn't because it's just radical, it's because it's what we call a radian measure. Radian measure is something you guys learn about in Algebra 2. It's kind of like, you know how the metric system is worldwide? And we use just inches and feet and all that kind of stuff in America. It's kind of the same idea with degree measure. Degrees are usually kind of a basic unit of measure. Most people deal with what's called the unit circle, and we deal with it in terms of pi. Okay? So if you go all the way around a circle, how many degrees is that?
180. 360.
360. If you go a full circle is 360 degrees. So from 0 to 360, which means in terms of radian measure, you don't have to worry about this right now, that means it's 2 pi revolution. Those two mean the same thing. So if I go halfway, I'm at how many degrees? 180. So instead of being at 2 pi for full revolution, I go half of it, I would be at pi. What's half of 180? 90 degrees. So what do you think half of pi is? Pi over 2. So in most worlds, in most upper level math classes and whatnot, we deal with this in terms of pi measurements and radian measurements like this. It's actually extremely simple to follow through once you guys learn about, which you'll learn next semester, about the 2 triangles that create this whole circle. It looks like it's going to be a nightmare, but ladies and gentlemen, you're going to like this stuff because most students like math problems that have an algorithm to it. You know what I mean by an algorithm? An algorithm is a method to solve. Use this method each and every time, it will always work, that kind of thing. To convert with these things, it's the same thing each and every time. It's very hard to mess that up. Whereas when we have eventually we'll start talking about proofs, where you have more than one way to set up a problem, more than one way to get to an answer, students have a hard time grasping the idea that it's okay to use your own adventure, choose your own adventure to get to an answer. You might take a longer route than somebody else, and that's okay. And you guys have friends that are in Algebra 2 right now, they're working with systems of equations. Systems of equations with 3 variables. Yes.
They do that?
Yeah. So it takes a little getting used to, because if you go off one direction, it might be a little bit more difficult than one other direction. But it's the idea that there's no one size fits all for a lot of these types of problems, whereas when we convert things, it's one way and you do it and you're fine. So anyway, we go back to classifying angles by their degree measures. What is one type of an angle? A right angle. All right. What is a right? Oops, I know how to spell the word right. A right angle is 90 degrees. Good. It's an angle who measures angles. Actually, I'm going to show you a way the book writes this. M angle. What do you think that stands for?
Measure.
Measure of the angle equals 90 degrees. Do you know what symbol they use for that when you're looking at a diagram? Do you remember? For showing a right angle? Remember what it looks like in a diagram? Yeah, exactly. You'll see it like this, where in a diagram it'll put this little box. That little rectangle, that little square in the corner, that means it's square. When things are square, they measure 90 degrees. Acute angle is another one, yeah. What's that? Oh, I just put that little dot. You know what? Here's the other thing. Let me go show you. I know where you're getting at this one now. You guys remember this one, acute angle?
Yeah.
It's less than 90 degrees, but it's greater than what? 0, thank you. So it's a measure of an angle. Actually, we do it this way. The measure of the angle is greater than 0, but it's less than 90. Mr. Allen, you were asking me about, I forgot to put my units in there for the measurement there.
No, I just couldn't see it.
Oh, it's okay, because 90% of the time I forget to put the little dot there when I'm talking about degree measure. Is it really the end of the world?
No.
No, it really isn't. Okay? To be honest with you, in a perfect world, I would love everything to be labeled absolutely flawlessly perfect. But hey, if I can get you guys to remember that an acute angle is between 0 and 90, I'm okay with that. And then remember, hi!
Oh, gosh.
How are you? Good to see you. Have a great day. So, do you guys remember the other way to remember that? I don't know who that is. Remember the other way to remember about acute angles? Because they're little. They're cute. Because they're little. What? You never heard that before? Thank you. You guys are mean. Obtuse. What's an obtuse angle measure? You're right, it measures 130. Okay, I'll give you that. It's an obtuse angle. But what is it? Over 90, but less than? An obtuse angle is more than 90, but it's less than 180. In this class, we probably will not ever deal with angles greater than 180 degrees. I honestly can't remember any problem in this book or worksheet or anything that deals with the angle measures greater than that. Yes, sir? I don't, but if you want to take the thing to the bathroom and grab some toilet paper, help yourself. And then the last angle measure one is what? Do you remember? What's the one we're missing? What? Straight, very good. The straight angle. G, what do you think a straight angle is going to measure? 180. Okay. So you have the 4 different types of angles. You got acute, obtuse, right, and straight. When we walk through these things, it's not so much a matter of having to prove or solve or do anything of that craziness with those things. It's a matter of, can you identify what type of an angle something is when you're done with it? That kind of stuff, okay? You were mentioning isosceles. Isosceles, when we get into the triangles, And then there's specific properties of that later. That's not until November-ish, I think, somewhere around there, end of October. We start worrying about isosceles and things of those properties, okay? Not so bad so far? Call me crazy, but I'm pretty sure all this was review, right? I think you've all seen this before. So like I said, I know you guys have seen this. It's not anything crazy. Which gets us to be able to do this. Angle addition. Hey, angle addition, what do you think this is going to mirror itself from? What's that? No, say it. Go ahead. Adding. Gee, you're right. What did we just get done adding together a couple of days ago? Starts with an S and ends in an segments. Segments, very good. So do you think that segment addition is going to be the exact same thing as angle addition? Yes. I was waiting to see how long I was going to wait to get somebody in here. Guys, segment addition and angle addition are the exact same thing. Two smaller segments add up to equal the whole. Gee, what do you think is going to happen with two smaller angles? They add up to equal the larger. That's it. It's the exact same thing. So if I look at this, two smaller angles add together to make a larger. One thing though, must have same vertex. That is the only thing that has to happen. Just like with segment addition, they had to be collinear. Here they have to have the same vertex. So when you think about what we did last week and then into this week, we did segment addition. Angle addition is the exact same thing, but at an angle. That's it. So writing it out is what's going to look different. Everybody agree here that the common vertex for the three different angles we have here is going to be B? Yeah. In long form, if I'm going to write out the two small angles equal to large, it looks weird because you have so many letters in the symbols. That's the only messiness of angle addition. You can get lost in the letters. So in this example, I could say the following. Angle ABD plus angle DBC equals angle ABC. And that's all it is. The two smaller angles add together to get the large. Notice all three of them have the same middle letter. They're all the same vertex. That's the kicker. You have to have the same vertex for it to work. And that's really the worst it's going to get is that you might get lost in the letters. That's all. The math is the same. The algebra is going to be the same. I think more often than not, they still use the same numbers, same variables, and all those parts, just in a different section number with a little bit different diagram. Okay? So let's say in this example we had angle ABD. Let's say it was 34 degrees. And the whole angle was 112. And I wanted to figure out how much that angle is. What would you do? That's it. See how it's the exact same thing as segments? You're just turning. It's the exact same problem. Okay. What I would do is I know that it would be the 34 plus something equals the 112. And I just subtract the 34. Let's see. 78 degrees, I believe. It's the same problem. Okay. You guys look like you don't believe that it's going to be the exact same stuff. You're worried for it. Are you? It's okay. You can direct. You can subtract. It's by all means. The only thing is, I'm saying, what happens if there's variables for it? That's all. I'm just showing it up the long way. Right. Let me show you another one. So in this case here, we have two smaller angles, EFG, or excuse me, EFH and HFG, and I need to figure out, I've got the two small, and I gotta figure out the large. What do you do? You add them together. What is 37 plus 19? 56. So your angle measures itself out to be 56 degrees. Okay. Again,
What you just said?
I couldn't understand what you just said. You were yelling something.
No, but you added that, right?
Yes, sir.
That's what I said.
What do you went?
No, because I choked on spit. I don't know what happened.
Very well. I'm not like making light of this too much, am I? Or are you guys okay with this? I'm hoping it's pretty straightforward. So now things might get a little messy. Does it say that they're the same? Nope. It does not say that they're the same angle, so I can't set them equal to each other. But it does say that the large angle equals 78 degrees, and you have two of the smaller chunks. Yep. Yep. Notice it's the exact same problem as a segment addition. Really, the only thing that changes is that since they gave you a degree measure, they put a degree symbol in it as opposed to it equals 78 centimeters or something. That's it. So when you write this out, do you need to necessarily write out all of it in letters? Or could you just go ahead and write down the algebra? Either way is okay. Yes, sir.
What happens if you're given like for NRP, like you'll be given an AX plus 7,
Uh-huh.
and then like you won't be given the PRQ, you gotta find the whole thing, and that whole thing.
Then it'll be a different problem. There's other ways of going about it. It depends. Each problem is going to be independent of itself. Okay? So there'll be times where, you know, like for this example here, it's asking you to find PRQ. So you'd have to solve for X and then substitute back in. Okay? That's the algebra part of it. Just like we did with the segments, it wasn't just solve for X, it was find segment XY, something like that. Okay? So we still do the exact same thing. We know that this angle plus this angle has to equal the whole thing, so you write it out. 8x and 7, 4x minus 1 is 78. Once again, we are back to the combined like terms. So what's 8x and 4x?
12x.
7 minus 1.
6
Okay. So we have a 12x
plus 6 equals 7. Minus 6 on both sides. 12x equals 72.
and then
12 divided by 2.
oh, other way around.
Yeah, 72 divided by 2. Or you just divide 12.
And what do you get? You get 6. Bless you. But back to the same idea as we did before. It wasn't always just solve for x, it was solve for a part of the problem. In this case, it's asking for PRQ. So what do you do with that 6? Yeah, we just substitute back in. So what is 4 times 6? Subtract 1 and you get, there's your answer. Okay? It's, like I said, it's the same thing we dealt with the segments. It doesn't change. Okay? It doesn't change. Depends what the question asks. Sometimes it's going to ask you to find all 3 of them. Sometimes it might just ask you to find 1 of them, 2 of them, whatever. Okay, so always, each question is different. You always got to read it. All right? Let's try another one. Boy, oh boy, angle bisector. What do you think that looks like?
A bisector, what in an angle?
So go back to Go back to what a segment bisector did. What did it do?
It met up at the midpoint.
Correct. Therefore, what did it do to the segment?
It made a four.
No.
Wait, no.
Cut it in half.
Yeah.
So what do you think an angle bisector is going to do?
It's gonna cut the angle in half.
Exactly. So it cuts it into two congruent equal angles. So an angle bisector cuts an angle into two congruent angles. Yes, sir. So again, like we did before, it's what do we call it? A segment bisector. It went through the midpoint, and it could have been anything. It could have been a point, a ray, a line, another segment. Angle bisectors are generally going to be another ray. That's all. It's the easiest thing that they usually draw with these things when you're talking about angles. It's usually another ray that comes up through it. So an example of that would be just looking like this. There's my angle. We'll call it A, B, C. And if I put in another ray, and I call it ray BD, if BD bisected ABC, what are the two angles that are congruent? ABD and?
BDC.
I can't say BDC because that's not my angle. DBC. And then we just mark it. Remember how we used tick marks before?
Yeah.
Now we use those little arcs like that. Okay? That's when we start using those. Those types of tick marks. So if this was 48 degrees, what is that one? 48 degrees. And what's the whole thing then? 96 degrees. Yep. That's all it is. That's all it is. It's the exact same stuff.
We're not in the homework.
What's up?
We're not in the homework.
We'll get there. We'll get there. Like I said, and that's why, I'm like I said, I'm not trying to make light of this stuff because I know that it really is a lot of review from what we do with the segments. It's just, you're turning. That's it. The math part doesn't change. Like you like poke it in, like try not to say, you can knock, it's okay.
Well, I thought you saw me, so.
Well, I wasn't sure it was you or not, because I just saw some, it's like,
I didn't know.
you're hiding behind the wall going, so here's the other thing that happens. In this case here, it says BD is the angle bisector. And I want you to pay attention to how they wrote this out. They said that angle ABD is 11x minus 12! Woo! Because it's got an exclamation point. It's really not yelling at you. It's just for some odd reason. I'm just trying to mess with you. I'm not mad at you. I do this all the time. It's not yelling at you. The typesetting, for some reason, on the worksheets from time to time will have an exclamation point instead of a degree symbol. I don't know why. Somebody was asleep at the switch when they were pressing buttons, and they never went back and fixed it. So
Can we just put the degree symbol?
it's fine. And to be honest with you, if you don't have the degree symbol, it's not the end of the world. So if it's a bisector, if it's an angle bisector, what do you know about those two angles? They're equal. So if I have to solve for x, if these two are equal, what do I do algebraically? That's it. You just set them equal to each other. Very good. So we set them equal to each other. 11x minus 12 is 8x plus 3. And you're back to another variables on both sides of the equation, two-step problem. Just like we did with segments. So pick on the little guy. What are you going to move? 8 or 11? 8, good. Subtract the 8x. Now, people were asking me in first hour, like, Murphy, why do you always want to move the little one? I'm like, well, if you move the big one, then you have to deal with negatives. And you don't want that, because you want to deal in positivity, not deal with negativity.
I never thought about it like that.
Plus, you'd be less likely to screw up, too.
Yeah, because if negative stuff is in your life, then you're just gonna screw up.
Sure. And at the same time, I'm going to add 12 back and forth as well. So now I'm left with what? 3x and a 15? What do you get for x? Now, don't forget, it's not only just solve for x. I think this question asks for find the measure of ABC. So if you have to find the measure of ABC, what do you do with the 5? Yeah, you go right back into the equation, into both angles to make sure you didn't screw up. So if I substitute x here, what's 11 times 5? What's 55 minus 12?
3.
I do it again. 5 up to here. What's 8 times 5? And, all right, pace yourself here. 40 plus 3.
45.
Oh, get out of here. So what's the whole thing then? Remember, I'm always going to substitute into both angles that have been bisected to make sure I get the same number. Because if I don't get the same number, I know I screwed up. Which means I know to go back and fix it. The whole thing, the ABC is, that's the whole part here. The 43 is just this part, and the other part is the 43. That's where we get the 86 from. Okay. Anything? Well, I don't remember. I want to check this real quick because I talked about that in the first hour, but I think I actually put the diagram in instead of using it for tomorrow. Just want to verify. So the other quick thing to remind you guys of, this won't take very long, and then we'll be done. Now, one last example for you. Sometimes you're going to have to work with diagrams that have big diagrams that have lots of parts to them. Now, one of the things that I would suggest that we do is that we work with an easy spot to start with. For example, when I draw these things together, when two lines intersect, and I'm just going to look at the right side of this diagram real quick. When two lines intersect, how many angles are formed? 4. 4 of them. You have 2 on one side and 2 on the other. No matter what side you choose, what do these two angles here and here have to add up to equal? What do these two have to add up to equal? What do these two have to equal? What about those two? So, what is A? Yes, sir.
Isn't like,
Aren't they equal?
acute and obtuse, isn't obtuse like big?
Yes.
And then like acute is like little?
That's what we talked about, yes.
They
I
could
just
be-
got that, because obtuse is like obese.
There you go.
It's like big.
Where is it? B and 160. And we'll talk about why those two are equal tomorrow. So as I go through something like this, I just pick a spot to start. You guys agree that it has to be 180 to get up to here, so it's 20. I go back here and it's again 160. What do you think that's going to be?
20.
Do you know why those things opposite each other are equal? What happens is those are called vertical angles. We'll talk about that tomorrow as one of our angle pair relationships. It's just anytime you have a pair of opposite rays that create lines, opposite angles then are equal. So it's really easy to show. What does this box mean?
90 degrees.
Right.
So if that's 90 degrees, what do all three of these angles have to add up to equal? 180, good. If this much was 90 here, how much has to be between these two then? It also has to be 90, and you're right, C will be 15. So a lot of times what people will do is they'll draw this box in right away, because then I know that 75 and C have to add up to equal 90. Therefore, C is 15. Now, when you have two lines that intersect, and if one of them is a 90-degree angle,
The bottom.
what do you know about all of them?
All of them are 90 degrees.
They're all 90-degree angles.
Oh, I got it. So it's like that. It's 90 degree angle, but if it's like that, it's 180.
Correct. But aren't two 90-degree angles together 180?
Yeah.
So again, going back to the other side here, I know that this has to be 90. These two are opposite one another, which means this one has to be, which means this one is. Homework-wise, I already have it on the calendar there for you. Let me pull it back up. I had it open. It's again in the book. I tried to do a link right to the page, and I don't know if it worked or not, so if it didn't, it's no big deal. But I'd like you to do those problems for tomorrow. It's page 29. There's 22, 27, 29 through 31, and then 33 through 42. Most of them, there's a good chunk of them. I think there's like 33 through like 39. 6 of them are off of one diagram, just like the example we just did. It should not take you more than 15 minutes tops to do all of these. You will fly right through. Okay? Give those a shot. You got time right now. We got about what? 8, 9 minutes. You want to get through a few of them without so much of a hassle. Okay?
Mr. Markley?
Yes, ma'am.